Hello and welcome back to this series on NER, or Named Entity Recognition, in Python for the purposes of the digital humanities. In the last video, we looked closely at word vectors, and we saw what word vectors were and what they looked like when plotted out on a two-dimensional graph. For those of you who don't remember, word vectors, or word embeddings, are mathematical representations of a neural network's or machine learning's vocabulary. So the way in which it understands words. And if you don't remember, the closer word embeddings appear typically indicate similarity or similarity in context. So words that are used in tighter clusters, or words that are in tighter clusters, are typically used in similar ways or have similar contextual meanings, such as Gryffindor being closely aligned to the words tower, Slytherin, Ravenclaw, Hufflepuff, because they're all houses in Harry Potter. In this video, I'm going to show you how to take a corpus and generate custom word vectors. I am going to be providing the data for doing this. In the upcoming series, which will start in January of 2021, I will be going through and showing you how to prepare proper data for processing via Gensym, and I will be talking extensively about the Gensym library, which is good for other things such as topic modeling. So the first thing I need to talk about is the data. What should the data look like? Ideally, your data should look like this. And what this is a very simple hierarchy. It is a list in a JSON file. This could be a list stored in any other way. Within that list is a series of segments. So these will be a set of lists delineated, as normal lists are, by commas. Within that list, that nested list, will be a collection of words. So word one, word two of that segment. So if you imagine a sentence that looks like this, Tom was a child, and then you had period, Jerry was a mouse. These are two sentences in an entire corpus. The corpus would be broken up like this. You would have a list to delineate both segments in that text, which in our case is going to be the sentence, and then what you would have is a nested list within that list, and it would look like this. Tom was a child, and then you would have a comma and another list, and that would be this sentence broken up by individual tokens or words. Now, there's a bunch of different ways to achieve this, and in my series on Gensym, I'm going to show you how to properly prepare a corpus for processing. For our purposes, though, I'm going to presume that you already have your corpus delineated in this way. So a JSON file or something that looks like this. And I'll be providing you with this JSON file. This is a JSON file of the entire corpus of Harry Potter, properly prepared for generating word vectors. There are a few mistakes in it that I'm not proud of, but it'll work for our purposes. So that's all you really need. The other thing that you'll need, and I'll provide this as well, is a JSON file of what we call stop words. Stop words are a common concept in NLP, or natural language processing, and I encourage you to get familiar with it now. Stop words are words that have meaning in sentences, but occur so frequently that they oftentimes throw off machine learning models when generating word embeddings or word vectors. Things that are included in this list vary depending on the software framework that you're using. In this case, this is a list of stop words for the English language that come from the NLTK, or the Natural Language Toolkit, which I believe is still put out by Stanford. Now, notice in here that the first things we have are a series of pronouns: I, me, my, we, our, ours, etc. Pronouns are commonly included in stop word lists. Additionally, we have the verb to be, conjugated in all of its different forms. So is, are, was, were, be, been, being, etc. Then we also have other things such as reflexive pronouns. I believe I saw those in the list somewhere. So your whose, whom, etc. Then you also have your that, those, these, etc. And then you also have other things that just occur commonly. And these are typically well thought out and well cultivated lists. And I encourage you to use available stop words lists. You can find them by simply doing a search on GitHub. You can find them by doing a search on Google. I'll provide this stop words list with this entire GitHub page or repo. So that's all you really need to do. to actually do follow along with this series is get that corpus and get the stop words. And let's go ahead and jump right in and start by importing the libraries that we're going to need. Because all of our data is stored as JSON files, we are going to be importing JSON. If you're not comfortable using JSON, it's okay. Go watch my videos on JSON files and you'll feel a lot more comfortable. You'll know how to use them. They are a key component of working with data outside of Python. I encourage you to, even though they look scary, to just try to get used to them. The other thing we're going to do is we're going to import a few things from the Gensim library. If you haven't pip installed Gensim yet, go ahead and do that now. So we're going to do from gensim.models.word2vec, we're going to be importing the word2vec. And then we're also going to be grabbing from gensim.models.keyed vectors, there we go, import keyed vectors. So this word2vec is going to be how we create and output word vectors via Gensim. We're going to create a word2vec model and output the word vectors. And this is going to allow us towards the end of this video to check for similarity between words that are in our vocabulary, our model's vocabulary. And this is going to be optional. Import multiprocessing. Multiprocessing is a built-in standard Python library, and it allows for you to use multiple CPUs in your computer to perform tasks much more efficiently and much more quickly. It's useful if you know how to do custom multiprocessing, but the good news is Gensim has built-in multiprocessing. It just needs you to import the library, and you can access and use multiple CPU cores. So if you have a 10-core CPU, you can run 20 threads, which is kind of allows for you to essentially do things 10 times more quickly. So we're going to start by creating a function, and we're going to only pass in one thing to that function, and that's going to be the model name, the name that we want to give to our information. We're also going to be opening up our corpus, which in this case is going to be HP-JSON. I'm going to be using HP-JSON, which is just the first two books divided up in the way I said, because it's going to allow me to prototype and demonstrate how this all works much more quickly. We're going to just open that up as read and encoding UTF-8. That's not entirely necessary, as I know that I don't have it encoded, or I don't need to specify the encoding because it's an obvious encoding that Python will figure out by itself, but it's always good practice to specify it. It'll save you a little bit of headache. And so as always with our functions, we're going to just load in the data, and it's always good to, let's just call this HP model 03. I've run this a few different times. Let's call it HP-NER underscore model 03. And that way I can keep this model a little separate from the ones I did when I was prototyping before doing this video. So the first thing that I'm going to do is I'm going to test out the function so far and make sure that it loads up and runs correctly. And we should see the text outputted. And we see that right here. The sentences of the first two Harry Potter books broken up into words that have had the stop words removed from them, and the sentences rendered as a list of words. Fantastic. We know that that bit of the function works. We don't have to really kind of go through and debug that anymore. The next thing we're going to do is we're going to say that sentences is equal to texts. Now, I know what you're probably thinking. Why did I not just do that right here? This is going to be code that I use in my tutorial series on Gensim, and so that I can keep the code from that tutorial series consistent with this one, in which we have to change these variables up a little bit, I'm going to put that here. Include that now. You don't have to. You could just load this in directly as sentences. Either will work for our purposes. The next thing we're going to do is we're going to grab the number of cores that our computer has. Now, this will vary based on the computer that you're using. This is an entirely optional component. If you don't feel comfortable using multiprocessing or you don't want to, simply skip this step. That one single line of line 16 and the one argument that we're going to pass that tells the model how many cores to use. And after you do that, it's time to start just building the word2vec model. Now, we're not going to include bigrams or trigrams in this model. It's not going to be robust. Bigrams are words that occur frequently together, such as French and revolution. French means one thing, revolution means one thing, but when used together, they become a bigram. That means something very distinct and unique. So French Revolution is a specific revolution that took place in France in the 18th century. but we're not going to include those in our model. The way bigrams and trigrams work in a model is they are incorporated as unique entities or unique words in its vocabulary. So we are going to pass in a few arguments to this word2vec model. And for this, I'm grabbing essentially the parameters that are included both in the GenSim documentation and on a Kaggle blog post that I'll be sharing in the comment section down below. So we're going to pass in min count, and I'm going to set this equal to 5. What min count does is it takes it removes words that don't occur by anything less than the frequency of the minimum count. So if a word doesn't occur 5 times, it's not going to be included in our model's vocabulary. Because typically you would have a higher number here, but because our vocabulary and our corpus is so limited, I would recommend playing with this number. I've played with it from anything from 1 to 5. I went up as high as 20, and I found that it actually threw off the model significantly. The next thing I'm going to pass is the window. And for this, I'm going to stick with the documentation of 2. This is essentially the words around the word that it's currently analyzing and trying to get a sense of, so the window of understanding. The size is going to be the dimensionality of each individual word. So if you ever hear the term, the shape of your word vectors, this will oftentimes be 2 numbers. It'll be the shape. The first number will be it'll be in a tuple like this. It'll be the size of the vocab, and then it'll be followed by the dimensions of the vocab. So this will usually be 300 to 500, somewhere in that range. I've gone as high as 5,000 with certain problems. The dimensionality increases the ability for the model to harmonize a larger vocabulary and bring words closer together and have a better understanding of a word's meaning. I encourage you to spend time and play with this, what we call parameter. And the adjustment of parameters on a little level, so having a loop where you have a model that is 500, then the next loop is 501, 502. This is called adjusting hyperparameters. But for right now, stick with a size of 500. I have found that that works good with this small data set. So we're going to have sample is going to be equal to 6e minus 5, and I'm not going to get into explaining what sample or alpha actually are. They deal with the learning process. In my tutorial series on GenSim, I'll explain these a lot more in depth. For now, just put them in there. This is all dealing with the parameters of actual learning. Negative is going to be equal to 20. And then this is the part where you can leave out if you are not going to be doing multi-processing. This is the number of workers, so the amount of cores that you're going to be harnessing while training your model. And believe it or not, after that, it comes time to simply go through, build the vocabulary, and train the model. So what we're going to do is we're going to call that word2vec model object, and we're going to start building the vocabulary, and we're going to pass in one argument to build that vocabulary. We're going to pass in our argument of texts or sentences, depending on what you want to actually use. So we can use sentences here, or we can use texts. I'm just going to continue using texts for right now. So we're going to say word2vec model. We also want to train that model. Now comes the time to pass in some parameters for training. The first thing that we want to give it is the corpus. So our list of sentences broken down by words. The next thing that we want to give it is the total examples, which is going to be equal to word2vec model.corpus count. And then finally, we want to tell it how many times to train. So how many generations. Each generation will go over the entire corpus, examine it, and harmonize those word vectors. With each successive generation, in theory, you get better word vectors. There is a point where you actually have an overfitted model or a model that performs poorly. So play around with the number of epochs. 30 is typically is a good starting point. This is kind of a industry standard, if you will. The next thing that we need to do is we need to save our model. Now, it's not entirely necessary to save the model here, and the reason for that is because we're not interested in the GenSim model. We are, however, interested in the word vectors. The reason why we're saving the model right now is so that we can see the similarity and explore the the word vectors through the Jensen model. And that's going to make a lot of sense in just a second. So we're going to save it like that, and we're going to use an F string, and we're going to pass in, which is a formatted string, and then we're going to pass in that model name that we're passing through all of this function. Oops. That's going to throw that off. There we go. And the next thing that we need to do is we need to actually save the word vectors themselves. So we're going to say wtv underscore model dot wv, so word vectors dot save word to vec underscore format. I know these functions are a little long, but they're necessary. So word vectors, and we're going to say word to vec. This is my naming convention. We're going to, again, pass in model name, so we have the consistent name. In our case, it's going to be this HP underscore NER underscore model underscore 3. And then when we run this, it's going to go through very quickly and read in that entire corpus and actually go through and train our model. And there's other things you could do to kind of, make sure everything's running correctly. But if you look with this small corpus, it's already done. So I've got the model over here saved, and I've got these word vectors saved as well. And as you might expect, Harry is at the top of the list. It's a book about Harry. This first line tells us the size of the vocabulary, so the shape of the vocab, and the number of dimensions. So we have 5,801 words, unique words in this corpus. These are non-limitized, so we have not found the root. That is a step that you could take to possibly get better results, possibly have consistent results. It's really up to you to play around with these parameters. So that's what these mean right here. And so what we now can do, now that we have the vectors produced and the model trained, is we can create a simple function for analyzing the similarity of the words in those vector space. Because as you might imagine, reading all of these vectors, this is what a word vector looks like, 500 floats that are actually one-dimensionally reduced matrices of themselves, all kind of put out in this long list. For a human to read this would be, I wouldn't even know where to begin. But fortunately, we can use the computer to tell us what all those word vectors mean by simply writing a simple function for getting the similarity. So we're going to say gen similarity, and we're going to pass in one argument for this. And that's going to be the word that we want to analyze. So our goal in this function is to give the function a word and have outputted the most similar words. So let's go ahead and try to do that right now. So we're going to say model is going to be equal to, and we're going to say keyed vectors. So we're going to call that keyed vectors function that we imported earlier. Load word to vec format. And here we're going to pass in simply the model that we were working with, or the word to vec HP NER model 03.txt. And we're going to say binary is equal to false. The next thing we're going to do is we're going to say result is going to be equal to model.most similar positive is going to be equal to word. Word. There we are. And then what we're going to do is we're going to print off the results. And what it's going to allow us to do is essentially get the words that have the closest meaning to a given word. It's best if we just kind of explore this. So let's do similarity, call that function, and we're going to pass in the word Harry. Now, in theory, we should have words that are used most frequently around Harry. And it'll take just a second to run, and we see that we have the words that are used most frequently around Harry are Ron, quickly, Ginny, Hermione. So we actually have some pretty things that one would expect. You've got an adverb here, which you could eliminate because apparently Harry Potter quickly does things quite frequently. We also have Ron, Ginny, and Hermione all kind of appearing in there as words that occur frequently around Harry Potter. And so that's kind of essentially the result of the model training word vectors. And these are the words that appear most closely around Harry. So let's pass in another one. From the last video, we looked at the word Gryffindor. Did I spell that correctly? I hope I did. Gryffindor. Apparently I didn't. Oh, it's got two F's, I believe. Gryffindor? There we go. I have to actually Google this. two Fs. There we go. So we're going and looking at the word Gryffindor. Now, one would expect to see things associated with Gryffindor, and in fact, we do. The word tower, Ravenclaw, team, Slytherin, so the Gryffindor Quidditch team, Slytherin, and Hufflepuff. So we see these clusters of meaning around Gryffindor look pretty good, quite like what one would expect. Gryffindors, plural. And like in the last video, we see already, even though we're only training on 2 books from Harry Potter, we're seeing the words points and Quidditch being associated closely with Gryffindor, because as we discovered in our 2-dimensional plot, that was the way in which Gryffindor was frequently used, was in association with Quidditch. And so you can play around with these hyperparameters. So you can go back through and retrain the model to include, I changed the minimum count to 1 here, to include every word from your corpus. So don't leave anything out. We want to see everything. So right now, this is going to take a little longer to train, but not much longer, because we're including as many words as we possibly can. And I expect that 5,800 number will probably go up. And this is occurring so quickly on my computer because I have 10 cores minus 1, so I'm using 9 cores to actually train this model. But when it's done and it's fully trained, it'll replace our previous word vectors, and in theory, it should also output a result for the most similarity to Gryffindor. And in fact, what we're seeing is something a little bit better. By changing that word count to 1, we see that Tower, Slytherin, and Hufflepuff and Ravenclaw are now all very closely aligned with Gryffindor. In fact, if we go back and we look at just Harry again, I imagine we'll see Ron and Hermione closer to Harry, as opposed to Ginny and Quickly. This is just a guess. We will see. Ron, Quickly. We still see Quickly there, but we see Hermione is moved up now. She's closer. Ginny is further back in all of this. And this comes down to the fact that we've simply changed the amount of words that are allowed to be harmonized in our word vectors or our word embeddings. And if I pull this up, which is taking just a second to load, we will see that the dimensions of our word vectors has now, in fact, changed. And instead of 5,800 or whatever it was before words, we now have 18,000 unique words, because we're including all those words, even those words that only appear 1 time in the first 2 Harry Potter books. So that's essentially how you go through and generate word vectors and test word vector similarity. In the next video, I'm going to show you how to use these word vectors to inject them into a blank spacing model that we will then, in the next video, start training as a custom NER model. That's going to be it for this video, though. Thank you for listening, and if you've enjoyed this video, please like and subscribe down below.